Hi, this is part 3 of my homemade VIC-II replacement project, or at least my efforts to try and replace the 6567 and 6569 video chips in the Commodore 64. If you haven't seen parts 1 and 2, they're available on my channel. I'll put links in the description below. So I went ahead and had this board fabricated by pcBWAAAaaaaaaay. It has 5 bus transceivers between the headers and the socket. On the bottom I stacked a few sockets in order to clear the shield that surrounds the VIC-II socket on the motherboard. This is just a ground wire so I can hook up the ground of my oscilloscope probe. And on the side is a video out header that I made to be pin compatible with my HDMI adapter board that I have. It can do 12-bit RGB. And this is the Mojo V3 FPGA development board that I talked about in my last video. It has a Xilinx Spartan 6 FPGA. There's a microcontroller on board, some flash RAM, USB, power jacks. It's discontinued, but they're still on eBay. You can find them. So the board is basically a hat for this dev board. So you connect the two like this. There you go. And now we just connect the this is the HDMI adapter that I have, and just plug that in to the side. And that's pretty much it. This plugs into the VIC socket of the Commodore 64. This is just a prototype still. I didn't pay any attention to how this thing would fit, so it's still way too bulky to fit inside a closed computer. But that's not really important right now. And so yeah, that's worked out pretty well. So here it is installed in my breadbin. This is PCB model 250407. It's one of the earlier breadbin models, and this is the model I've been testing with. And as you can see, I like I said before, I didn't really pay much attention to how this was going to fit. It kind of extends beyond the port where you would expect the cable to come out. I think the expectation here would be that if you were going to use an HDMI out, that you would remove the RF modulator, because otherwise it's kind of hard to get the cable out of a closed computer. And since RF modulators aren't really useful anymore, you might as well remove that. But it's still too early to think about stuff like that. I just really wanted to get off of the breadboard version of this, and this has been working out pretty well so far. It's much more convenient to use this than the breadbin. I can plug this into other boards as well. And I have plugged this into a shortboard version, and normally the two boards, the chips that go in them, are not compatible. The older breadbin boards delivered 12 volts and 12 volts to the VDD pin, while in the short boards that went into the 64C versions, they delivered 5 volts to the VDD pin. But in this case, that pin isn't even hooked up. The FPGA will operate on 5 volts on the VCC pin regardless, so this actually works in both the short board and the long board. So that's convenient. And let me just go ahead and flip it on here and hit the reset switch and focus, and there it is in glorious HD. So I have hooked up here, I'm running it off of the DC power jack here. I don't have to do that. I do have a jumper on this board that lets me power it off of the motherboard entirely, so it could be closed up if you could get the cable out. But this is convenient for me because I can turn off the computer, keep it powered, and then plug in the USB jack to upload new bit streams. And that way I don't have to keep unplugging it and plugging it back in. Otherwise I would send 5 volts into the motherboard when I didn't want to, and I'm not sure if I would want to program this thing while it was powered on. So this way I can power off the 64 and still program the board, and it's just convenient that way. So to make sure that the core is as accurate as possible, what I've been doing is I've been running these test programs that were written by the VIC team to catch regressions in the emulator. And what you're seeing here is a report that's generated from a script that I wrote that runs VIC along with my special hooks that drive my FPGA simulator. If you recall in my first video, I described what I put together to exercise the core on my PC, just to make sure that I can render frames and make sure that they look the same. So what you're seeing here on the left is a screen capture from what VIC produced, and on the right is what the FPGA core will produce. And aside from the colors, you get a pixel for pixel match. I still only have 3-bit color on the FPGA, and it's a bit darker, and some of the shades of gray are a little bit different there, but the pixels match, which is what's important. So I'll just scroll through some of these to show you what they look like. They're basically testing a bunch of edge conditions and different cases to make sure that the logic is right and the timing is right. And some of these tests are interactive, so they're meant to be run on the computer, where you press keys to change various inputs. And so here's an example of one that tests that timing is right with regards to the foreground color change. So if I click on this, I can bring up the VIC version, click on the FPGA one, and then I can flip between the two and just make sure that it's a pixel for pixel match. And aside from the colors, and it's a match. So if I keep going, so out of the 280 tests, 278 are a match. And this is one of the ones that didn't match, but I ran this on a real 6569, and this is what was produced. So for some reason VIC is adding this white line here, but that doesn't actually show up on the real thing, and so I'm not really sure where that's coming from. So I count that as a pass. And if I just scroll down here, just look at some more interesting ones. So a lot of these are just simple screenshot tests, and they look like they're a match. I'll just scroll down to some other interesting ones. So this is the one that did not match, and there's a slight difference here. I'm not sure where that's coming from. I did run this on the board that I have on the machine that I'm testing with, and it does look like this more or less, but there are some slight differences, and I'll just have to investigate where that's coming from. But this is the only one out of them that didn't match. This is the FLD scroll. This is working pretty well. And let's see some other ones that I can get down to. So this is testing like sprite crunch routines and other various color register changes, some timing tests, and let's just go down to another one that's interesting. So this one exposed some issues in the core that I managed to fix. What this is doing is it's changing video mode on the fly, and just making sure that if I go to the VIC one and the FPGA one, you can see it's a match now. So that was a troublesome one. Keep going. Some sprite routines, sprite crunch again, and some of the tests actually tell you what to expect. So in this case, even though there are actually 4 sprites that are active here, but because of the timing, you only see the third one. And again, same thing for here. And here's, you see the first 3, but not the last one, and just a bunch of different tests. And occasionally you'll see an NTSC version of the test, and those are off center because of the different vertical and horizontal blanking interval that I have in the core, but the screen does match, just off center a bit. And so yeah, this is looking pretty good. It's these ones were also, the sprite split tests were also kind of a pain to get working. It requires precise timing, and so in this example here, while it's rendering a sprite, they're changing the expanded and unexpanded register kind of halfway through, and just make sure that the pattern matches, which would indicate that you're handling that register change at the right time. And so they do things like that with expanded, unexpanded, multicolor, high res, and changing different registers and making sure that that the pattern matches. And you can see that they run through the same sprite in different positions. I think like each of the 8 positions in a cell, to make sure it lands, the register change lands at the right spot. So yeah, I'm pretty happy with that result. This is looking pretty good. I think I can say it's probably close to 99% accurate now. At the end here, I threw in some snapshots from other from demos that I had issues with in the past. So this is the introduction to Edge of Disgrace, which is the the grid pattern that you'll see. This is the sprite crunch hand that comes out. One of the transition sequences. This is again Edge of Disgrace. This is Crest Stage, and this one is an interesting one. These are 50 pixel wide sprites, and interestingly a 9th sprite in the bottom right there, which is a weird one. There's the massively interleaved sprite crunch routine, which is now working. It works just fine. The previous glitches I had weren't actually noise like what I thought, but they were actually the sprite collision registers not matching properly. So I fixed that up, and now this runs well on the real thing. There's Super Mario Brothers, and then some more of uncensored, and then finally my own X scroll test to make sure that X scroll is working properly. So this is looking pretty good. I think it's behaving pretty well. I've run many games, and they all seem to get handled. Demos do get handled fine. It's just I still have that what I think is a noise issue causing an occasional glitch or jam. So this is one of the test programs that I mentioned before. This is called raster hold, and the idea here is you get a stable raster at the top of the screen, or raster interrupt at the top of the screen, and it's supposed to be a black bar at the top, which it is right now. But I had noticed that every once in a while it would start to flash and flicker a different color. So I looked at the source code for this, and what you're seeing there is that color is essentially represents the bits, the lower 4 bits of register D019, which are the interrupt register, or the sprite collision bits, and raster interrupt and light pen. And I noticed that it would flash a brown color, and that would mean that the light pen bit was getting flipped. And on this test, it should not be changing. So I'm just wondering, what's going on there. I started to investigate, and right now it's not happening. And I think it's not happening because the machine is cold right now. I just booted it up after having been off for a while. And what I'm going to do now is just let it sit here running and see if the status changes. Okay, so it's been running for a while, and what I did is I hooked up the oscilloscope to the clock and the light pen line, and that light pen line is hooked up to the joystick port 1, pin 6, which is the fire button, and it's also hooked up to pin 14 of the first CIA chip. And I just noticed something really odd, is that the voltage level on that is quite low. And this noise on the clock is something that I've been fighting with. You can see that when the signal, or right after the edges, there's this ground bounce or signal reflection, or there's just this turbulence, and I think that's happening due to the I guess the fast edges of these transceivers. If I look at the clock that the FPGA is producing, it actually looks quite clean. There it is there. So there's very, like that blue line there, it's not really that turbulent, but what you're seeing on the yellow there is what the CPU is seeing, and that's on the other side of the transceivers. So that's something I really need to investigate, but I think what's going on here is that light pen low voltage, it must be just at the threshold of what that transceiver considers high or low. And if I look at the pin, what the FPGA sees, so that's on the FPGA side of the transceiver, so that's where this light pen glitch is coming from. And I think that swing there on that purple line, which is the light pen, is just so high that it's triggering a high-low switch there. And so this might be, I'm not sure if this is a normal voltage coming out of the CIA chip, so what I'm going to try and do is swap the CIA chips and see if that makes a difference, because I tested the voltage coming out of the same pin on the second CIA chip, and it's looks like a healthy 5 volts, and I'll see if that makes a difference. Okay, so I swapped out the CIA chips, or I swapped them in the board, and sure enough that same pin is showing a nice healthy 5 volts. And what the FPGA is seeing now is a solid high. So that was the problem. I think that CIA chip is on the verge of failing. So by swapping them out, or by swapping them, I probably just created a different problem. But I might just change to a different board to continue testing. But I think this is solved the mystery for me. It's probably the cause of another program failing. The FLD scroll test was also glitching, and I know that test also uses the light pen interrupt. So that kind of explains what the glitches are. So I'm just going to do a test now with this CIA chip swapped and see how it goes. Okay, so this is the FLD scroll test program, and it's an interactive program. And what you do is you hit W and Q to change, or to do the scroll. And if you put the first number between 21 and 29, then that gives you this flexible line distance effect, and you can scroll text an arbitrary distance away from the top there. And you can see this. Well, this used to glitch out on me like crazy, and now that I've swapped the CIA chips, you can see it's working perfectly. And I can go through all the different numbers, and it seems to be working pretty well now. So I think that's one of the pitfalls of using these old computers. Chips are on the verge of failing, and I think I might have to source a new CIA pin or a CIA chip to get around this problem. So just to summarize what was happening there, I was running this test program called raster hold, and that black bar, it's supposed to represent the contents of register D019, which is the register that holds the interrupt status bits. So that's sprite collision, raster interrupt, and light pen interrupt. And it's supposed to be black, which means the lower 4 bits should be 0, but it was flashing brown every once in a while, and that meant that this value was 8, which is the color of brown on the 64, which meant that the light pen was triggering unexpectedly, and that ended up leading me to this low voltage situation on pin 14 of CIA U1, and probably wouldn't normally have been an issue on a real 64, but on my board, since there was this noise, I think it was causing this voltage to swing, and it was registering high and low during that time. And so I'm going to rerun some of the tests on the demos that I've run before that have glitched occasionally, and one of them was uncensored. And I'm not sure if this was really the cause, but I think the real cause might have been, or might be, this noise that I mentioned earlier. I think it's either switching noise, or the edges off the bus transceivers are too fast and are causing some sort of reflection or ringing on the line. And it seems like the CPU deals with it for the most part. but I have seen the occasional glitch every once in a while, and I'm wondering if that's the cause. And I'm sure this is a problem that electrical engineers have figured out, and they could probably solve this real easily. But like I said before, I'm not an electrical engineer, so maybe if somebody watching this knows of something I can try. I've decided to do another version of the board because I made some mistakes on the board, and I think I've hacked away at it enough. And I'm going to make some changes to the board, so I might be able to address this if I know what to look out for. So my last test with uncensored still ended up in a CPU jam as before, so that light pen issue wasn't the problem. Then I decided to try and run it on this board, which has a real 6569, and to my surprise, it also crashed on this machine, and Edge of Disgrace also crashed. Or sorry, it crashed on Edge of Disgrace, but it glitched on uncensored in much the same way that it glitches on the FPGA board. So I'm wondering if I'm just chasing another real-world problem with the board, since it also seems to fail on a real 659 or 6569 chip. And I'm pretty sure that this chip doesn't have the VSP bug. I've been running this VSP tool, which is supposed to detect that VSP problem, and it doesn't look like it's crashing during VSP. It doesn't look like it anyway, so I'm not really sure what's going on there. But I know these demos, they push the 64 to its limits, and I'm wondering if it's just another issue where some component on the board is just aging and it's not able to keep up anymore. I know that the FPGA core will handle the demos okay as long as the the inputs are good, but I think maybe a combination of the noise or some other problem on the board is causing those glitches. It doesn't seem to happen with games. Games seem to run okay. I don't think I've ever experienced a crash or major glitches on games. So this is a list of the games that I've been testing with, and aside from the one issue that I had with Mayhem and Monsterland, occasionally I would get the opening sequence or the credit sequence to show garbage sometimes. The game did play okay, and it didn't always happen, but that's the only glitch that I've seen. All the other games you see here, they ran fine, and I don't expect to have problems with games. They don't seem to punish the VIC chip like the demos do. So that's been, I think, pretty good results out of this homemade board. So like I said, I still have these noise issues. When I measure the outputs from the FPGA, they look pretty clean. Like I get clean signals. I set the Spartan 6 has a quiet I/O slew rate, which is the slowest slew rate. I set it to be the slowest or the lowest current, which is 2 milliamps. But then when I measure the outputs from these 74 LVC4245 bus transceivers, the outputs are quite noisy, and especially around the time that the two address bus transceivers switch. And I don't really know why. It might, like some people have suggested that it might be that the edges are too fast, and I don't think I can have any control over the slew rate of those transceivers or the current, and that might be the issue. It's just that it's too fast, and there's this something weird is going on, and I don't really, I'm not qualified to really speak to it. I just see it on the scope. If there are any electrical engineers out there that have some ideas, I can try. Let me know. I can send you my PCB design. Maybe you can see something obvious in there, and you can have some suggestions. But despite these noise issues, I'm pretty happy with the performance of it. It seems to only glitch out or crash on these intense demos, and like I've discovered, they also crash on real 64s, even 64s that don't have the VSP bug. So I'm wondering if it's just old hardware that can't keep up anymore. Not sure. So next steps, like I said, I've kind of abused this board, and I think I'm going to make another prototype board in order to fix some mistakes and maybe try some new things, and maybe I'll order a couple of them this time. just to have a backup. And so I have to make a decision, like whether I could just stop here. It could just be, the hat is on this Mojo V3 board is the thing that you could put together if you're really interested. But it doesn't really make for a good solution if you want to close up the board, because it's still pretty bulky. I think I'll start thinking about a single PCB design, maybe based off the Mojo V3 FPGA board. Kind of basically remove the headers, add my own video port. In the ideal solution I would want is to be able to software switch NTSC and PAL. Right now the bitstream has whether it's NTSC or PAL hard coded in there, and the clock multiply divider parameters are just hard coded in there. So I would like to be able to switch that, and that would mean some sort of configuration utility that you would run on the 64 that maybe would talk through some custom registers to trigger things like changing the chip model and the video standard, and maybe a custom palette would be nice too. As for composite things, that kind of complicates things. I did put together a board that produced produced the Luma Chroma signals, and I fit it back into the board like I had planned, but the picture was quite dark, and I think that there was a mismatch in voltage levels there. I did get a picture, and so the idea did work, but it also complicates things in that you need 2 accurate color clocks. So you need the 4 times color carrier signals, and they have to be pretty accurate. Otherwise, you get this color shimmer, especially on PAL displays. And sometimes, if you're way off, then the CRT won't even lock onto the signal. If you don't have composite, then you don't really need the color clocks, and you don't have to be super accurate in terms of the dot clock. So that would add some complication to a board, but it's kind of, I still like the idea of having a board that you could just plug in and close up the machine and then just have it work the way it did before, which would mean being able to produce the Luma Chroma signals. So someone had asked whether there was a GitHub repo for this project, and there isn't yet, but I do intend for this to be open source eventually, and hopefully open hardware too. I will continue to plug away at this, but I may have reached the limits of my abilities here. Once I start getting into electrical issues, then I might have to tap the community for some help, but I will continue to keep trying and hopefully come up with another update soon. All right, thanks for watching.